question number 15, and this question is part B question. And let f power 2 plus f is equals to 0, where f is entire function and f power n implies nth derivative of f. Now in question, which of the following statement is true? Option 1, limit n tend to infinity, fn at 0 is equals to 1. Option B, limit n tend to infinity, fn at 0 is equals to minus 1. And sequence of fn at 0 where n belongs to set of natural number is convergent, and option D is this. Now come to explanation of this question. As we know that f power 2 plus f is equals to 0, where f is entire function, this can be written as d power 2 plus 1 into f is equals to 0, where d is a differential operator with respect to x. Now for solution, put d is equals to m. This implies that m square plus 1 is equals to 0. This implies that m is equals to plus minus iota. And now the solution of a differential equation, f belongs to ls, that is linear span, where s is equals to set of sin x comma cos x. Now according to given question, or for simplicity, case first fx is equals to sin x, and case 2 fx is equals to cos x. And case first, if fx is equals to sin x, this implies that fn x is equals to sin of x plus n pi upon 2. At x is equals to 0, fn 0 is equals to sin n pi upon 2. Now in sequence form, f1 0, f2 0, f3 0, and so on. Now as we know that the value of sin n pi upon 2 for n is equals to 1, 2, 3 and so on, this implies that sin n pi upon 2 in sequence form 1 0 minus 1 0 1 0 minus 1 0, and this implies that this sequence is a bounded sequence, and set of all limit point of this sequence is minus 1 0 1. This implies that the sequence fn at 0 not convergent, because it has no unique limit point. As we know that a bounded sequence is convergent if it has unique limit point, but this sequence has more than one limit point. This implies that this sequence is not convergent. So option A incorrect, option B incorrect, and option C incorrect. Now for option D, as we know that sequence or mode of fn at 0 is equals to sequence 1 0, this minus convert to 1 using this mode, and 1 0 1 0 1 0. Now take the odd subsequence of this sequence, and we get 1 comma 1 comma 1, that is constant sequence. This implies that convergent subsequence of this sequence. This implies that option D is correct. For verification, come to case 2, that is fx is equals to cos x. This implies that fn x is equals to cos of x plus n pi upon 2, and this implies that fn 0 is equals to cos n pi upon 2. Now in sequence form, cos n pi upon 2 at n is equals to 1 2 3 and so on, this implies that 0 minus 1 0 1 0 minus 1 and so on. This implies that this is a bounded sequence, and but it's a not convergent. Same logic, because it has a not unique limit point. This implies that sequence fn 0 is not convergent. This implies that option A, B, C are incorrect, and option D is correct. Now option A is incorrect, option B incorrect, option C incorrect, and option D is correct. Now come to next memory based question, and this question is also from part B. In question, let fn from closed interval 0 comma 1 2 are such that fn x is equals to n plus 2 into n plus 1 into x power n into 1 minus x for every x belongs to closed interval 0 comma 1. Now in question, which of the following statement is true? Option first is sequence fn is divergent on semi-closed interval 0 comma 1, And option B, Fn is a pointwise convergent sequence but not uniformly convergent sequence. Option C is Fn is uniformly convergent sequence. And in option D, limit n tend to infinity of integral 0 to 1 of fnx dx is equals to integral 0 to 1 of limit n tend to infinity fnx dx. Now come to explanation. As fnx is equals to n plus 2, n plus 1 and this for x is equals to this, and we can say that fx is equals to limit n tend to infinity of fnx is equals to 0 identically. That is fx is equals to 0. And we know that this fx is a pointwise limit. This implies that sequence fnx is a pointwise convergent sequence. This implies that option A is incorrect, because in option A we have given that sequence fnx is divergent. Now come to option D, that is limit n tend to infinity integral 0 to 1 of fnx dx is equals to integral 0 to 1 limit n tend to infinity fnx dx. As we know that from the previous explanation, limit n tend to infinity fnx dx is just fx. So this whole integral can be written as integral 0 to 1 fx dx. Say this side left hand side and this right hand side. Now come to firstly right hand side. As we know that fx is equals to identically 0. This implies that integral 0 to 1 fx dx is equals to integral 0 to 1 0 into dx. This implies that 0. Now come to left hand side. Limit n tend to infinity integral 0 to 1 n plus 2 into n plus 1 x power n into 1 minus x dx is equals to limit n tend to infinity n plus 2 into n plus 1, because these are constant for this integral, because integral with respect to x. So integral of x power n into 1 minus x is equals to x power n plus 1 upon n plus 1 minus x power n plus 2 upon n plus 2 0 to 1. This implies that left hand side is equals to limit n tend to infinity n plus 2 into n plus 1 bracket 1 upon n plus 1 minus 1 upon n plus 2. Further, after simplification, this implies that limit n tend to infinity n plus 2 into n plus 1 into 1 upon n plus 1 into n plus 2. This cancel with this. This implies that 1. This implies that left hand side is equals to 1 and right hand side is equals to 0. So this implies that option D is incorrect. Now for option C, we have to remember the result. That is, if fnx sequence is uniformly convergent to fx in closed interval 0, 1, this implies that limit n tend to infinity of integral 0 to 1 fnx dx is equals to integral 0 to 1 limit n tend to infinity fnx dx. This must be equal to this. If this sequence is uniformly convergent, this implies that this integral must be equal to this. But from previous explanation, this integral not equal to this. This implies that fnn sequence is not uniformly convergent. Now come to options. Option A is incorrect. Option C is incorrect. Option D incorrect. And this implies that option B is correct. And this question is from part B. Question is, suppose A and B are two similar matrices, that is, there exists an invertible matrix S such that A is equals to SB S inverse. Now, which of the following statement need not be true? Actually, in this question, we have to find out the statement which in general not true. Options are minimal polynomial of A is equals to minimal polynomial of B, trace of A is equals to trace of B, and A transpose is similar to B transpose, and last option, range of A is equals to range of B. Now for this question, now come to explanation. As we have given that matrix A is similar to matrix B, that is, there exists an invertible matrix S such that A is equals to SB S inverse. This also implies that matrix B is equals to S inverse AS. Now, if matrix A is similar to matrix B, this implies that the characteristic polynomial of matrix A is equals to characteristic polynomial of B. and minimal polynomial of A is equals to minimal polynomial of B. As we know that if a characteristic polynomial of two matrices are same, this implies that both the matrices have same eigenvalue. That is, every eigenvalue of A equals to every eigenvalue of B. Now, as we know that trace of A is equals to sum of its all eigenvalues, this implies that trace of A is equals to trace of B. Now, option A and B are incorrect because in question we have to find out that option which in general need not be true. So option A and B are incorrect. Now come to option C. As we have given that matrix A is similar to B, that is there exists an invertible matrix such that A is equals to SB S inverse. Now apply transpose on both sides. This is equals to A transpose is equals to SB S inverse transpose, that is equals to A transpose equals to S inverse transpose B transpose S transpose. Now that S is invertible matrix, that is S inverse is equals to identity matrix. Now apply transpose on both sides, that is transpose and transpose. This is equals to S inverse transpose. S transpose is equals to identity matrix transpose is equals to same identity matrix. This implies that S inverse transpose is equals to identity into S transpose inverse. This implies that S transpose inverse is equals to S inverse transpose. So after this simplification, this implies this. Now this implies that A transpose is equals to S transpose inverse into B transpose into S transpose. Let for simplicity S transpose is equals to P. As we know that S is invertible matrix, this implies that P is equals to S inverse is also invertible matrix. Now this implies that A transpose is equals to P inverse B transpose P. This is a definition of similar matrix. This implies that A transpose is similar to B transpose. That is, option C is incorrect because in question we have to find out that option which in general need not be true. So this implies that option D is correct. Now come to further explanation. Also for option D, let a matrix A 3 cross 3 matrix 1 0 0 0 2 0 0 0 0. Now range of A is equals to column space of A, that is column space of A is the space which is generated by columns of A, that is generating set of these three vectors, that is column C1 C2 C3. Its generating set is equals to three tuple of x comma 2 y comma 0, where x comma y belongs to set of real number. Now let B matrix such that 1 0 0 0 0 0 0 0 2. Now range of B is equals to column space of B. As we know that column space of E is the spanning set of all columns of B, that is C1 C2 C3, and its spanning set is equals to all the three tuple of x comma 0 comma 2z, where x comma z belongs to set of real number. Say this star and say this double star. From star and double star we get range space of A is not equals to range space of B. This implies that option D is correct because according to given question we have to find out that option which in general need not be true. So option D is correct. Now come to options, that is option A is incorrect, option B incorrect, option C incorrect, and option D is correct. Now come to next memory based question of CSIR-NET and question number 20, and this question is from part C. Question is find the largest positive real number delta such that for the statement, that is if mod of x minus y less than delta, then mod of cos x minus cos y less than root 2, and options are 2, 3 upon 2, root 2, and pi upon 2. For this question we use the result, that is cos x minus cos y is equals to 2 times of sine of x plus y upon 2 sine of y minus x upon 2 less than del. We have mod of cos x minus cos y less than root 2, Using previous result, this implies that mod of 2 time of sine of x plus y upon 2 into sine of y minus x upon 2 less than root 2. After some simplification, this implies that a mod of sine of x plus y upon 2 into mod of sine of x minus y upon 2 less than 1 upon root 2, because this 2 when this side, that is 2 upon 2 is equals to 1 upon root 2, implies this. Now come to further. Now for mod of x minus y less than delta, this implies that mod of sine of x plus y upon 2 into mod of sine of x minus y upon 2 less than 1 upon root 2. Say this statement first. And as we know that mod of sine of theta, where theta is equals to x plus y upon 2 less than is equals to 1 for every xy belongs to R. Say this inequality 2. Now actually in question we have to find out the largest value of delta. So using 1 and 2, this implies that mod of sine of x minus y upon 2 less than 1 upon root 2. Actually for this we use greedy algorithm of largest value of delta. Now as we know that if mod of x less than a, where a is greater than 0, this implies that minus a less than x less than a. So using this we get minus 1 upon root 2 less than sine of x minus y upon 2 less than 1 upon root 2. Now applying a sine inverse in all side, that is sine inverse of minus 1 upon root 2 less than sine x minus y upon 2 less than sine inverse of 1 upon root 2. As we know that sine inverse of 1 upon root 2 is equals to pi upon 4, and sine inverse of minus 1 upon root 2 equals to minus pi upon 4. So using these two result, we get minus pi upon 4 less than x minus y upon 2 less than pi. Now multiply this inequality using 2, we get minus pi upon 2 less than x minus y less than pi upon 2, and we can write this inequality in a form of modulus, that is mod of x minus y less than pi upon 2. Now compare this with our condition, that is delta is equals to pi upon 2. So we get option incorrect, option B incorrect, option C incorrect, and option D is correct. This question is from part C. Question is let f from R2 to R such that f x comma y is equals to x power 1 upon 3 into y power 1 upon 3. Now in question, which of the following statement are true? Actually in this question we have to find out the true option. Now options are function is, that is f is continuous at 0 comma 0, and function is not differentiable. Fx does not exist at 0 comma 0, where fx means first order partial derivative of f with respect to x, and the last option is the directional derivative of f exists at 0 comma 0 in some direction. This wording is important for this option. Now come to explanation. For this question, if function is continuous at 0 comma 0, this implies that a limiting value of function at 0 comma 0 must be equals to its functional value, that is f 0 comma 0 must be equal to this limiting value. Now from given function f 0 comma 0 equals to 0 into 0 equals to 0, simple. Now check its limiting behavior. This is equals to limit xy tend to 0 comma 0 x 1 upon 3 into y 1 upon 3, which is equals to 0, because as we know that limiting behavior of x power p into y power q for p greater than 0 and q greater than 0 at limiting 0 comma 0, this value equals to 0 always. Now from this result, this implies that its limiting value equals to 0. Now from this and this implies that limiting value of function at 0 comma 0 equals to its a functional value, which is equals to 0. This implies that function is continuous at 0 comma 0. This implies that option A is correct. Now come to further discussion. As fx 0 comma 0 means first order partial derivative of f with respect to x. Now in journal, its original definition is this, and under simplification this become this. Now from given function, this value 0 and this value also 0. This implies that limit s tend to 0, 0 minus 0 upon h, which is equals to 0. This implies that option C is incorrect, because in option C we have given that fx does not exist, but it exists. That is, option C is incorrect. Now similarly, for differentiability we have to find out the first order partial derivative of f with respect to y, that is fy 0 comma 0. Its original definition is this, and after simplification this become this. Now from given function, this value 0 and this value again 0. This implies that limit k tend to 0 of 0 minus 0 upon k 0. It's simple. Now from this and this implies that fx 0 comma 0 equals to fy 0 comma 0 equals to 0. Say this equation first. Differentiability of function at 0 comma 0, that is f 0 plus h comma 0 plus k minus f 0 minus 0 equals to h into fx plus k into fy plus square root of h square plus k square into phi of h comma k. This is a function of two variable. Now result is if limiting value of phi hk at 0 comma 0 equals to 0, this implies that our function fx comma y is differentiable at 0 comma 0. And if its limiting value at 0 comma 0 is not equals to 0 either, or does not exist, this implies that our function fx comma y is not differentiable at 0 comma 0. Now after some simplification, fh comma k minus f 0 comma 0 equals to h into 0, because fx is equals to 0 plus k into fy is equals to 0 plus square root of h square plus k square into phi. Now further this implies that h power 1 upon 3 into k power 1 upon 3 equals to square root of h square plus k square into phi. And this implies that phi is equals to h power 1 upon 3 into k power 1 upon 3 upon square root of h square plus k square. Now for differentiability of function, we have to find out the limiting behavior of phi at 0 comma 0, that is limit h comma k tend to 0 comma 0 of h1 upon 3 into k1 upon 3 upon this. Now for this limit, we use a path, that is h is equals to k. Actually this path is y is equals to x line, so h comma k tend to 0 comma 0 equivalents to h tend to 0 simply. Now using this path, this limit become limit h tend to 0 h power 1 upon 3 into h power 1 upon 3 upon square root of h square plus h square. This is equals to limit h tend to 0 h power 2 upon 3 upon under root 2 modulus of h. This limit does not exist. Okay. This implies that function is not differentiable at 0 comma 0. That is, option B is correct, because in option B we have given that function is not differentiable at 0 comma 0. Now for option D, that is for option D, we have to find out the directional derivative at some direction. That is, as we know that directional derivative of f at a point that is 0 comma 0 in a direction of u1 comma u2 is equals to limit s tend to 0 function of 0 plus h comma u1 comma 0 plus h into u2 minus f 0 comma 0 upon h. Now for simplicity, is equals to 1 and u2 is equals to 0. This implies that d1 comma 0 f 0 comma 0 equals to limit s tend to 0 f h comma 0 minus f 0 comma 0 upon h. From previous discussion, we noticed that this is the definition of fx at 0 comma 0 and this value is 0. This implies that directional derivative of f exists at 0 comma 0 in some direction, because there exists at least one point in which directional derivative of f exists at this point. That is, option D is correct. Now come to options again. Option A is correct, option B is correct, and option C is incorrect, because fx is exists at 0 comma 0, and option D is correct because directional derivative of f exists at 0 comma 0 in question number 22. And this question is from part C. Question is, for a given order of group, which of the following classification is are possible, and options are this. Now in this question we have to find out the possibility of classification for a given order group. For this question, firstly we have to understand the concept of class equation of a group of finite order. Now class equation of a group we means the representation of order of G equals to 1 plus 1 plus 1 up to order of ZG times plus summation of order of conjugate class of A, that A not belongs to ZG and A run over each conjugate class in G. Now result second, as we know that ZG, that is center of group, is subgroup of G. Then by using Lagrange theorem, order of ZG divide order of G. Result third, that is order of Na is equals to order of G upon order of conjugate class of A, where A belongs to G. Now N of A means set of B where B belongs to G such that B commute with A, and conjugate class of A means set of B where B belongs to G such that B relate with A. Now result fourth is, as we know that center of group, that is ZG, is a subgroup of Na for every A belongs to G. This implies that by using Lagrange theorem, order of ZG divide order of Na. Now come to further explanation. For option A, we have given that 14 is equals to 1 plus 1 plus 2 plus 2 plus 2 plus 2. This implies that we notice that from this class equation, order of ZG is equals to 2 because 1 repeat 2 times. That is order of ZG is equals to 2. Now this 2 implies order of conjugate class of A where A not belongs to ZG. Now for A node belongs to ZG, order of conjugate class is equals to 2. And now using result 3, order of Na is equals to order of G upon order of conjugate class of A. This implies 14 upon 2, that is equals to 7. Now result 4, ZG is a subgroup of Na for every A belongs to G. This implies that order of ZG divide order of Na. This implies that 2 divides 7, but this is not possible. This implies that this classification of a 14 order group not possible, that is option A is incorrect. And for a 14 order group the result is either order of center of G is equals to 14 or order of center of G is equals to 1. Also using this result, this option incorrect. Now come to option B. In option B, we have given that 15 is equals to 1 plus 1 plus 2 plus 3 plus 3 plus 5. From this classification, we notice that order of ZG is equals to 2 because 1 repeat 2 times. Now we know that ZG is a subgroup of G. Then by using Lagrange theorem, order of ZG divide order of G, that is 2 divide 15, but this is not possible. This classification is not possible, that is this representation of 15 order group is not possible, that is option B is incorrect. We can also use result, that is if order of group is 15, that is 3 into 5, order of ZG in this case always 15. Also using this result, we can discard this option, that is we can say that this option is incorrect. See, we have given that the class representation of 21 is equals to this, that is 21 is equals to 1 plus 3 plus 3 plus 7 plus 7. From this classification, we notice that order of ZG is equals to 1, that is ZG contains only identity element of a group. Now for conjugate class, that is A not belongs to ZG, that is A not equals to identity elements. Result 3, order of N is equals to order of G upon order of conjugate class. This is equals to 21 upon order of conjugate class, which is either 3 or 7. This implies that 7 or 3. Now from this information, it is clear that all the results 2, 3 and 4 are satisfied. So we cannot say anything about this class equation. Now for this we also have a result. As we know that if order of group is equals to 21, that is equals to 3 into 7, it have only two possibility, that is abelian or non-abelian. If a group is abelian, this implies that its class equation is this, because if abelian, this implies that G is equals to ZG, order of G is equals to order of ZG, that is one repeat order of ZG time, that is one repeat 21 time. Now if G is non-abelian, this implies that its class representation is 1 plus 3 plus 3, 7 plus 7. I have proof for this class equation, that is, for this proof, firstly we have to remember the result, that is if order of G is equals to n is equals to PQ form where P and Q are distinct primes such that P less than Q, then one class equation of G, that is order of G is equals to 1 plus P repeat Q time plus Q repeat Y time, that is for a 21 order group, is equals to 1 plus 3x plus 7y, that is 3 repeats x time and 7 repeat y time. Now come to proof. We have given that G is a non-abelian group of order 21. This implies that by using a Silo third theorem, G has a unique 7 Silo subgroup. G has a unique Silo 7 subgroup. That is, G has a unique subgroup of order. Also, G is a non-abelian group of order 21, and its generating relationship is A comma B, such that order of H 7, that is A7 is equals to E, and order of B is equals to 3, that is B3 is equals to E, and B inverse AB is equals to A square. In this proof, I use the concept of conjugate class because in a class equation, conjugate class concept is very important. Now, in a generating relation, order of H 7, this implies that A power 7 is equals to E. This implies that A comma A square comma A cube up to A6 are the element of order 7, because G has a unique subgroup of order 7 and G has 6 element of order 7. Now using generating relation B inverse A, B is equals to A inverse. Now from the definition of conjugate class, that is, in conjugate class, this is the mean, that is, this element belongs to conjugate class, but this element is equals to this implies that A square is belongs to conjugate class of A. Now in this relation, if we multiply, pre-multiply with B inverse and post multiply with B, this equals to B power minus 2 A, B power 2 is equals to B minus 1 power A power 2 into B is equals to A power 4. This implies that A power 4 belongs to conjugate class of A. That is, again iteration this steps and we get only 3 element in conjugate class of A. Similarly, conjugate class of A cube, this 6 element, this implies that there are only 2 conjugate class of order 3. That is, value of x is equals to 2. Now come to star equation, that is, we have 21 is equals to 1 plus 3x plus 7y. X is equals to 2 because we have only 2 conjugate class of order 3. From the previous discussion, this implies that 21 is equals to 1 plus 6 plus 7y. That is equals to 14 is equals to 7y and y is equals to 2. Now this implies that 21 is equals to 1 plus 3 into 2 plus 7 into 2. This is equals to 21. This implies that 3 repeats 2 time and 7 repeat 2 time. That is 21 is equals to 1 plus 3 plus 3 plus 7 plus 7. This implies that option C is correct. Now come to next option. Now in option D we have given that 39 is equals to, that is, class representation of order 39 is equals to 1 plus 3 plus 3 plus 3 plus 3 plus 13 is plus 13. We notice that order of ZG is equals to 1. That is, ZG contain only identity element and satisfy all the results 2, 3, 4 because for A node equals to LNT element, order of NA is equals to order of G upon order of conjugate class, order of G 39 and order of conjugate class either 3 or 13. This implies that 13 or 3. Now we cannot say anything about this classification, so we also have a result for 39 order group. If order of group is equals to 39, it's have only two possibility, abelian group and non-abelian group. For abelian group, we know that Zg is equals to G, order of group is 39. This implies that order of Zg is 39, that is one repeat 39 times. This implies that this is the class representation of abelian 39 order group. Also, if G is a non-abelian, in this case class representation of a 39 order group is this, that is 1 plus 3 plus 3 plus 3 plus 3 plus 13 plus 13. I also have proof for this, that is proof is as we know that 39 is can be represented as 1 plus 3, that is 39 is equals to p into q form where p less than q. 39 is equals to 3 into 13 where 3 less than 13, that is 1 plus px plus qy where 3 repeats x time and 13 repeats y time. Now as we know that G is a non-abelian group of order 39, so by using Silo third theorem it has a unique 13 Silo C subgroup, that is G has a unique subgroup of order 13. As we know that if order of group is 39 and G is a non-abelian group, then G can be represented in a generating relation, that is A comma B, such that order of A is 13 and order of B is 3, that is A power 13 is equals to E equals to B power 3, such that B inverse is equals to A power. This implies A power 13 is equals to identity element. This implies that A comma A power 2 comma A power 3 comma A power 4 up to A power 12 are the element of order 13, because we know that if G has a unique subgroup of order 13, then G has phi of 13, that is 12 element of order 13. Now from given generating relation we have B inverse is equals to A power 3. This implies that A power 3 belongs to conjugate class, because we know that by the definition of conjugate class of A contain the element B such that B belongs to G and B relate with A. That is, we notice that here this B relate with A, that is B inverse mean B relate with A, that is A power 3 belongs to conjugate class of A. Now again pre multiply with the B and post multiply with the B inverse. This implies that B power 2 A B power minus 2 is equals to B A power 3 B minus 1 is equals to A power 9, because for A we have A3, now for A3 we have A9. This implies that A power 9 belongs to conjugate class of A. Again and again using the iteration, this iteration we get only 3 elements in conjugate class of A and order of this conjugate class is equals to 3. Similarly using the above technique we have 4 conjugate class of order 3. This means that x is equals to, from the previous discussion we have x is equals to 4. This implies that 39 is equals to 1 plus 3 into 4 plus 13y. After some calculation we have 26 is equals to 13y, that is y is equals to 2. This implies that as we have 39 is equals to 1 plus 3x plus 13y, this implies that x is equals to 4 and y is equals to 2, that is 39 is equals to 1 plus 3 into 4 plus 13 into 2. This implies that this 3 repeat 4 time and this 13 repeat 2 time, that is 39 is equals to 1 plus 3 plus 3 plus 3 plus 13 plus 13. And this match with our option D. This implies that option D is correct. Now come to option again. That is option A is incorrect, option B incorrect, option C correct, option D correct. Number 23 question is let f from c to c non-constant entire function such that mod of fz is equals to 1 for mod of z is equals to 1 and d is a open unit disk around 0, and question is which of the following statement is false. Actually this question is from part B, and in this question false option we have to find. This implies that out of 4, 3 are true and one option is false. Now options are f of c is equals to c, f has at least one zero in d, f has at most finitely many distinct zero in c, and the last option f can have a zero outside d. For this question we use a result. This is very important result for this question. Result is if function c to c be a non-constant entire function c to c non-constant entire function such that for mod of z is equals to 1, this implies that mod of fz is equals to 1. Now if a function satisfy this condition, this implies that f of z is equals to alpha z power n, where n greater than equals to 1 and alpha belongs to c and mod of alpha is equals to 1. Now f of z is equals to alpha z power n, where n greater than equals to 1. This implies that f of c is equals to c, and for zeros of fz, that is fz is equals to 0, this implies that alpha into z power n is equals to 0. As alpha not equals to 0, this implies that z power n is equals to 0, and this implies that z is equals to 0. This 0 belongs to d according to definition of d as defined in given question. This implies that fz has no 0 outside of d. Now come to options. We notice that f of c is equals to c, that is this option is true. F has at least one 0 in d, this option is also true. F has at most finitely many distinct 0 in c, this implies that this option also true. F can have a 0 outside d, this option is false, that is option D is correct and option A, B, C are incorrect. 24 question is consider f from R2 to R defined as fx comma y is equals to for x not equals to y, x minus y whole square into sine of 1 upon x minus y, and for x is equals to y function value 0. Question is which of the following statements are true, and this question is from part C. In this question we have to find out the true option. Okay, and options are f is continuous at 0 comma 0, f is differentiable at this point, and f has a partial derivative fx that does not exist at 0 comma 0, and fourth option, that is f has a partial derivative fx continuous at 0 comma 0. Now for this question, as we have a function defined this way, and for continuity at 0 comma 0, we have to prove that its limiting value of function at 0 comma 0 must be equals to its functional value, that is f0 comma 0. Now for value of f0 comma 0, we notice that x is equals to 0 and y equals to 0, that is x is equals to y, and we know that from given function x is equals to y function value 0, this implies that f0 comma 0 equals to 0. Now after this we have to check the limiting behavior of function at 0 comma 0. Now trick is that if xy tend to 0 comma 0, we have to notice that chosen any path gx comma y equals to 0 which passes through origin. Now limiting value of function at 0 comma 0 equals to limiting value of x minus y whole square sine of 1 upon x minus y such that x not equals to y. Remember this point. If x is equals to y, we not do this, we only do this for x not equals to y. Now this implies that limiting value of x minus y into limiting value of x minus y into sine of 1 upon x minus y. As we know that for any path gx comma y equals to 0 that passes through 0 comma 0. Now for this path which passes through origin, limiting value of x minus y as xy tend to 0 comma 0 always tend to 0. Similarly, limiting value of x minus y sine of 1 upon x minus y when xy tend to 0 comma 0 always tend to 0. This implies that whole limit tend to 0. This implies that limiting value function at 0 comma 0 equals to 0. This equals to function value which is equals to 0. This implies that function is continuous at 0 comma 0. This implies that option A is correct. Now as we know that fx 0 comma 0 equals to limit s tend to 0 f0 plus h comma 0 minus f0 comma 0 upon h. It's a predefined. Now this can be written as in this way. Now from the given function f0 comma 0 equals to 0 and f(h, 0) equals to h square into sine of 1 upon h, where h not equals to 0. Now this implies that fx0, 0 equals to limit s tend to 0 of h square into sine 1 upon h. This h cancel with this h because h not equals to 0. This implies that limit s tend to 0 of h into sine of 1 upon h is the standard result, and this limit always tend to 0. This implies that fx0, 0 equals to 0. Similarly, in this way, we say that fy0, 0 equals to 0, where fy0, 0 equals to limit k tend to 0 f of 0, 0 plus k minus f0, 0 upon k. Now come to further discussion. As for x not equals to y, function is this. Now partial derivative of this function with respect to x and this plus this implies that fx is equals to 2 times of x minus y into sine of 1 upon x minus y minus cos of 1 upon x minus y for x not equals to y. Now from previous discussion we have fx0, 0 equals to 0. Now we notice that the limiting value of fx as xy tend to 0, 0 does not exist because fx is equals to 2 times of x minus y sine of 1 upon x minus y. This limit exists when you apply xy tend to 0, 0, but this limit does not exist. That's why its a whole limit does not exist. This implies that limiting value of fx at 0, 0 does not exist, but its functional value exists. That is, fx is not continuous at 0, 0. Now for this question, we also have to check the differentiability of f at 0, 0. As we know that the procedure of differentiability in a two variable, that is f(h, k) minus f0, 0 equals to h into fx0, 0 plus k time of fy plus square root of h square plus k square into phi. Implies that h minus k whole square into sine of 1 upon h minus k is equals to square root of h square plus k square into phi. This implies that phi is equals to h minus k whole square into sine of 1 upon h minus k upon square root of h square plus k square. Notice this value phi. As we know that f is differentiable at 0, 0 if limiting value phi at 0, 0 tend to 0. Now from this we notice that this limit tend to 0 as h, k tend to 0, 0. That is, our function is differentiable at 0, 0. Now from given options, option A is correct, option B is correct. F has partial derivative fx that does not exist at 0, 0, but it exists. That is, we have fx0, 0 equals to 0. This implies that option C is incorrect. F has a partial derivative fx continuous at 0, 0, but not possible. That is, option D is incorrect. And question number 25. Question is, let R be a ring and n set of nilpotent elements of R. That is, n is equals to set of x belongs to R such that x power n is equals to 0 element for some n belongs to natural number. Question is, which of the following statement is true? Actually, this question is from part B and options are n is ideal in R, n is never an ideal in R. If R is a non-commutative ring, then N is not an ideal in R. And last option, if R is a commutative ring, then N is ideal in R. For this question, we have to recall the definition of ideal, that is a non-empty subset I is said to be ideal in R if and only if it satisfies two conditions. Condition first is for any a comma b belongs to I, a minus b must belongs to I. That is a plus b belongs to I and minus b belongs to I. Condition second is for any R belongs to ring and a belongs to I, R into a must belongs to I and a into R must belongs to I, where this implies left-sided ideal and this implies right-sided ideal. Now come to explanation. In option A, we have given that n is ideal in R. Now to check true or false. For this option, we take a ring that is a non-commutative ring of 2 cross 2 matrices with real entries, and take two elements A and B in R, that is A is equals to 0 1 0 0. This implies that A power 2 is equals to 0 element of ring. Similarly, B is equals to 0 0 1 0. This implies that B power 2 is equals to 0 element. This implies that A comma B belongs to N, because N is a set of nilpotent element. Actually, in this example, A and B are nilpotent element because there exist N is equals to 2 such that A power 2 is equals to 0 and B power 2 is equals to 0. We notice that A plus B is equals to 0 1 1 0, which is not a nilpotent element of R. That is, A plus B not belongs to N, because there does not exist n belongs to n such that a plus b power n is equals to 0 element, or we can say that 0 1 1 0 power n not equals to 0 element of R for every n belongs to set of natural number. This implies that uh, n is not an ideal. That is, option A is incorrect. Now for option B and C, we have two techniques to solve these options, that is direct result and this counterexample. This result says that if R is a non-commutative ring such that cardinality of out of R is equals to 1, then in this case a set of nilpotent elements form an ideal. Using this result, option B incorrect and option C incorrect. If we know for option B and C, we can also use this counterexample, that is cardinality of R is equals to 4 and R is a non-commutative ring without identity elements, and in this ring these two elements belongs to N, where N is a set of nilpotent elements and these two elements doesn't belongs to N because they are not nilpotent elements. Using this counterexample, we have N is equals to this, that is set of all nilpotent elements of R, and in this case N is ideal in R because it satisfies both condition. First, A minus B belongs to N and AR and RA both belongs to N. This implies that option B and C are incorrect. Now come to option D. In option D, we have given that R is a commutative ring. This implies that under second binary operation, x and y are commute. That is, x into y is equals to y into x for every x comma y belongs to R. And in question, we have given that n is a set of all nilpotent elements. And notice that n is a non-empty set because 0 element belongs to n. That is, 0 element is a nilpotent element. Now to prove n is ideal, let a and b belongs to n. If a and b belongs to n, this implies that a and b are nilpotent elements. That is, a power m1 is equals to 0 element and b power m2 is equals to 0 element for some m1 and m2 belongs to set of natural number. Now to prove n is ideal, we have to prove that A minus B belongs to N. That is, A minus B must be nilpotent elements. So for simplicity, I take A minus B power M1 plus M2. And using binomial expansion, this is equals to this series. And we get using this definition 0, 0, 0 and 0, which is equals to 0. This implies that A minus B belongs to N, that is set of all nilpotent elements. Now to prove second condition of ideal, let R belongs to ring and A belongs to N. This implies that A power M is equals to 0 element for some M belongs to set of natural number. Now Ra power M is equals to R power M into A power M, because R is a commutative ring. This implies that Ra is equals to AR. This implies that R power M is equals to 0 element. Further implies 0 element. That is R into A belongs to N. That is R into A is nilpotent elements. Similarly, we have to prove that AR is a nilpotent elements. That is AR power M is equals to A power M into R power M. Because R is a commutative ring, this implies that 0 element into R power M, 0 element. This implies that AR belongs to N. That is AR is a nilpotent elements. That is N is ideal in R. Our option D is correct. Now come to option. Option A is incorrect, option B incorrect, option C incorrect, and option D is